Dear students, welcome to second class on series. In the first class, we have seen the definition of series, sequence of partial sums, convergent series, divergent series, oscillatory series, related examples, and also we have seen geometric series, nature of the geometric series. Okay, in this video, we shall see some important results on series of positive terms. Before going to the results, first let us see what is series of positive terms. An infinite series sigma an is said to be series of positive terms if an is greater than 0 for all n is equal to 1, 2, 3, etc. That means sigma an is said to be series of positive terms if each term of the series is positive. Okay. So now moving on to the first result, theorem 1, statement of which is a series of positive terms either converges or diverges to plus infinity. Let us see the proof. First consider an infinite series of positive terms, that is sigma an is equal to a1 plus a2 plus etc plus an plus etc. Since this is an infinite series of positive term, each term of the series is positive, that is for all the values of n, an is greater than 0. Now I am taking n plus 1th partial sum of this series, which is given by Sn plus 1 is equal to a1 plus a2 plus etc plus an plus 1. See, in the RHS, sum of first n terms is nothing but nth partial sum. So RHS can be rewritten as Sn plus n plus 1. That is Sn plus 1 is equal to Sn plus an plus 1. Now take Sn to left side. What we get? Sn plus 1 minus Sn is equal to n plus 1, which is greater than 0. So now Sn plus 1 minus Sn is greater than 0 for all the values of n. Okay, take Sn to right side. Then we get Sn plus 1 is greater than Sn for all the values of n. Now, by definition of monotonically increasing sequence, sequence Sn is monotonically increasing. Okay. As of now, we are showed that sequence Sn is monotonically increasing. But what we need to show is this series converges or diverges to plus infinity. For that, I am considering two cases. First, case 1. Suppose that Sn is bounded above. Since already Sn is monotonically increasing, Sn is convergent. That is because we have one important result on sequences which says that a monotonic increasing sequence which is bounded above is convergent. By this result, sequence Sn is convergent. Now, by definition of convergent sequence, limit n tends to infinity Sn is equal to finite and unique. Now, by definition of convergent series, sigma an is convergent. Okay, let us move on to case 2. Suppose that Sn is unbounded above. Now, since Sn is monotonically increasing and not bounded above, it diverges to plus infinity. We have one result on sequence which says that a monotonically increasing sequence which is not bounded above diverges to plus infinity. So, limit n tends to infinity Sn is equal to infinity. This is by definition of divergent sequence. Okay, since it diverges to plus infinity, limit n tends to infinity Sn is equal to infinity. Now, by definition of divergent series, sigma an is divergent. Hence, series of positive terms either converges or diverges to plus infinity. Okay. Now, moving on to second result. which is necessary condition for convergence. Statement of this theorem is a necessary condition for convergence of an infinite series sigma n is that limit n tends to infinity an is equal to 0. This statement can also be put it in the form: if a series sigma n is convergent, then limit n tends to infinity an is equal to 0. Is the converse true? Let us see. Let Sn be sequence of partial sums of sigma n. We know that each series is associated with sequence of partial sums. Here Sn is sequence of partial sum corresponding to series sigma n. Suppose that sigma n is convergent. By definition, sequence Sn is convergent. That implies limit n tends to infinity Sn is equal to L, where L is finite and unique. Now I am writing nth term of the series. Nth term an can be written as a1 plus a2 plus etc plus an minus 1 plus an minus a1 plus a2 plus etc plus an minus 1. Right? See, this sum is nothing but nth partial sum, and it can be written as Sn, and this sum is nothing but n minus 1th partial sum, and it can be written as Sn minus 1. So an is equal to Sn minus 1, right? Now apply limit for this. What we get? Limit n tends to infinity an is equal to limit n tends to infinity Sn minus limit n tends to infinity Sn minus 1. But limit n tends to infinity Sn is L. So limit n tends to infinity Sn minus 1 is also equal to L. So now we have L minus L, which is equal to 0. Hence the proof. That is, limit n tends to infinity an is equal to 0. Therefore, if sigma an is convergent, then limit n tends to infinity an is equal to 0. Okay, let us see the converse part. The converse is not true. For example, consider the series sigma an, which is equal to sigma 1 by root n. Here nth term an is 1 by root n, and limit of the nth term will be 0. See here, limit n tends to infinity n is equal to limit n tends to infinity 1 over root n. If we apply limit to this term as n goes to infinity, this goes to 0. But consider Sn. Sn is nothing but nth partial sum of this series, which is 1 plus 1 over root 2 plus 1 over root 3 plus etc plus 1 over root n. Clearly we can see that each term of the series is greater than 1 over root n. So this sum is greater than 1 over root n plus 1 over root n plus etc plus 1 over root n. Since this is sum of n terms, this sum is equal to n times 1 over root n. Okay, so Sn is now greater than n into 1 over root n. We know that n can be written as root n into root n. 1 root n get cancels. So now we have Sn is greater than root n. Apply limit on both sides as n goes to infinity. What we get? Limit n tends to infinity Sn is greater than limit n tends to infinity root n. But this limit is infinity. So now we have limit n tends to infinity Sn is equal to infinity, which implies sigma an is divergent. Okay, sigma an diverges even though limit an is 0. Okay, converse part need not be true, right? Some of the consequences of theorem 2. First result, sigma an is convergent implies limit n tends to infinity an is equal to 0. Second one, limit n tends to infinity an not equal to 0 implies sigma an is not convergent. Third result, limit n tends to infinity an is equal to 0 implies sigma an may or may not be convergent. These are some of the important consequences of theorem 2. Okay students, see you in the next videos. Okay. Please keep watching videos regularly, make notes. Okay. Okay, students.